In this chapter, we also begin to talk about alkynes. And I want to remind you that alkynes are just molecules with triple bonds. And alkynes are named in exactly the same way as alkenes, except the ending YNE is used. So let's do some examples. So let's name this guy. So when we go to name this guy, we notice there are 4 carbons, 1, 2, 3, and 4. And so the prefix here would be bute here. And then there's a triple bond, and so it ends with YNE. And then we need to give the location of the triple bond. We want that to have the lowest number. And so we would count from this direction, right? Because if we count from the other direction, of course, this would end up with 3 as the number, and 1 is lower than 3. And so then the way we would name this would be 1-butyne, or sometimes you'll see it as but-1-ine. So you could see it either way. Let's do one with a substituent. So again, our longest chain here is going to be 4 carbons. That longest chain needs to include the functional group, which is the triple bond. And so again, this would be butyne. We need to tell the location of where that triple bond is, and then also the location and name of the substituent. So 1, 2, 3, 4. And so this would be 3-methyl 1-butyne, or you could name it as 3, I forgot an L there, methyl but-1-ine. Either way. So again, very, very similar to what we have experienced with naming double bonds. Now the physical properties of alkynes are very similar to alkanes and alkenes. They are insoluble in water. They're also less dense than water. They have very low melting and boiling points. So those are some of the physical properties. And when we talk about the chemical properties, they react similar to alkenes in addition reactions. Now, and so that would be something like if they were reacting with Br2, for example, H2, HCl. One of the differences, though, is they require twice as many moles of the addition reagents as the alkenes. And so the reason that happens is, for example, if we had CH3, CH2, CH here, and we reacted it with H2 and platinum, what we would see is that it would react to form then a double bond, but then it would also immediately react again to go on and form a single bond. Here. Same thing, for example, if you have CH3, CH2, C123, CH, and we were to react it with Br2, we would end up adding across the triple bond. And then it would react again across the double bond. Here, so it would react twice. And I left my 2 off. Don't be like me, put that 2 on there. So that's one of the big differences, is it will react twice. Now, the third kind of compound that we talked about at the beginning of chapter 12 were aromatic and compounds, and I want to compare those to aliphatic compounds. Now, some early researchers in organic chemistry really became intrigued by fragrant oils that could be extracted from certain plants. An example would be like oil of wintergreen or the flavor component of the vanilla bean. And the compounds that were responsible for those aromas had really similar chemical properties. And as a result, they were all grouped together and called aromatic compounds because they smelled. And as more and more aromatic compounds were isolated and studied, chemists gradually realized that aromatics contained at least 6 carbon atoms, had low carbon to hydrogen ratios relative to other organic hydrocarbons, and were related to benzene. Now, chemists also learned that the term aromatic wasn't always accurate. Many compounds that belong to the class, because of chemical properties and structures, don't smell at all, so they're not fragrant at all. And so when we think about aromatic compounds, right, most of these now, when we refer to aromatics, they contain the benzene ring, which is shown to the right, with alternating double bonds. So we see the benzene ring here shown with alternating double bonds, single, double, single, double, right? So they contain the benzene ring or its structural relatives. They contain at least 6 carbons, and they have a low carbon to hydrogen ratio relative to other hydrocarbons. Aliphatic compounds, on the other hand, are organic compounds that are not aromatic. So basically it's everything else. So these would include things like alkenes, alkanes, and alkynes. So hydrocarbons that are not aromatic. Okay. Now, one of the things to be aware of is that there are many fragrant compounds that don't have aromatic compound properties or structures. And so we still use that old class name, but it definitely has a different meaning. Now, let's talk about benzene for just a second. When we talk about benzene and we look at the structure of benzene, right, it has alternating double and single bonds. And so what we know is that double bonds are shorter than single bonds, and we can measure these. So when we went to measure these, as scientists, we expected a long, short, long, short, long, short. But we actually found was that all of these bond lengths were about the same, and it was somewhere in between the length for a single bond and a double bond. And so what we know now is that instead of those double bonds being localized or staying right where they are actually are spread out all over the ring, those electrons are. And so these are called delocalized electrons. Okay. And so this means that we tend to show the structure of benzene in a couple different ways. We can show the structure of benzene like that with the alternating bonds and knowing, and then we could also show it like this, knowing that that's the exact same thing. We've just turned it a quarter. We can show it with the little dashes here, but we can also show it as just a ring in the center. And so I just wanted you to keep this in mind because you'll see all of these different representations as the structures of benzene. Now, there are things, so benzene has a hydrogen on every single carbon, so one hydrogen on each carbon, and sometimes that hydrogen is replaced with other atoms, and we need to name those. So when we talk about naming benzene rings, we have some guidelines. So the first guideline is when there's a single hydrogen attached to a benzene ring that's replaced, the compound can be named as a derivative of benzene. So what do I mean by that? Well, for example, when we look at this molecule here, we see that this is an ethyl group. And so that name would be ethyl benzene. So one of the hydrogens has been replaced with an ethyl group. If we go to the next group, one of the hydrogens has been replaced with a nitro group, and so that would be nitrobenzene. Then one of the hydrogens has been replaced with a bromine, and so that would be bromobenzene. And then here would be chlorobenzene. Now, some common IUPAC accepted names are used preferentially over other possibilities. For example, if there's a benzene with a CH3, we tend not to call that methylbenzene. Instead, we call that toluene. If there's an OH attached, we call that phenol. If there's an NH2 attached, we call it aniline. And then if there's a C double bond OH attached, we call that benzoic acid. So these are what we could consider some common names that are the IUPAC accepted names. And so these really are 4 things you probably should commit to memory because we'll then continue to use them. Now, when the benzene ring is part of a more complex hydrocarbon, the benzene ring is referred to as a phenyl group, and it's treated really as a substituent. And so here are 2 examples. Here we can see that the benzene ring is 1, 2, 3, 4, is off the 4th carbon of a 7-membered chain. And so those are all single bonds, so that would be called heptane. And then we would say, look, that's for phenyl heptane. Sometimes benzene is shown as C6H5, like in the next example, and we would say, look, that's 1,1-diphenyl cyclobutane. Okay. So here are some examples of how benzene is named. Now, the 4th guideline is when you have 2 prefixes that are attached to a benzene ring, their positions can be designated by either numbers or ortho, meta, and para. I remember this when we look at this as if you've got something attached here at the top, it would be OMP, O-M-P. And so if it's right next to what's attached to the top, it gets the O prefix. And this can be shown a couple different ways. It can be drawn as O-dibromobenzene or ortho-dibromobenzene or 1,2-dibromo. benzene. So we have a lot of synonyms for the same thing. If it's at the 1 and the 3 position, it's M or meta. If it's at the 1 and the 4 position, it's P or para. And again, you can use the abbreviations, you can spell it out, or you can use the numbers as well. Then, right, if 2 or more groups are attached to the benzene ring, their positions can be indicated by numbering the ring so that you obtain the lowest possible numbers for the attachment. Now, if there's a choice of identical set of numbers, the group that comes first in the alphabetical order is given the lower number. And here's some examples of that. So, for example, we have bromine and chlorine. There you can number it 1, 2, 3, or 1, 2, 3, but we choose bromine as number 1 because alphabetically he comes first. We try to get the lowest numbering system, so this is 1, 2, 4 trichlorobenzene. And then here is an example where one of those names that we had before is embedded benzoic acid here. And when that's the case, it's assumed that benzoic acid is at 1, and then you would number where the 2 chlorines are. So let's look at some examples, and I'm actually going to get rid of this example. He came over, but we've already named him. So when we look at this first example here, what we find is that this example has toluene in it, so we can use that as the base name. So we come here and we say, great, that's toluene. And then we need to name the other substituent shown here. So we would go 1, 2, 3, and we would name this as 3-ethyl toluene. Then we would come over here and we would see that we have a substituent here, and this has 3 carbons. So that would be propyl benzene, for example. Or we could name it as 1-phenyl propane. Then, if we look down here at this next molecule that has 3 groups on it, we notice right here that we have a phenyl. Now, we also have the CH3, so you could name this using that toluene prefix, but if you have a phenyl, it's more likely to be named using the phenyl. And so we're going to use that as our base name. And then we're going to come here and say 1, 2, 3, 4, 5. Another reason why we're going with phenyl over the toluene is because that gives us overall lower numbers. So when we name this, this would be 2-isopropyl 5-methyl phenol. And so those are some examples of different ways that we will name aromatic compounds. And of course, we will do more examples in class. Now, let's talk about some of the properties of aromatic compounds. These are very similar to alkanes and alkenes and alkynes. They are nonpolar, so they're not going to mix in water, so they'll be insoluble in water. And so another way that we describe that is by saying they're hydrophobic. Okay. These aromatic rings are really chemically stable, and they do not undergo addition reactions. So they are very stable and do not undergo addition reactions. Okay. Now they will undergo substitution reactions, which we haven't talked about, where in each ring a hydrogen is replaced by some other group. Now, one of the derivatives of aromatic compounds are called polycyclic aromatic compounds. These are just where you have carbon atoms that are shared between 2 or more benzene rings, and so they form these linked rings just like this. So some examples here are naphthalene, which was the original active ingredient in mothballs, so it's responsible for that mothball smell. Then there's a number of more complex polycyclic aromatic compounds. Two of these are shown here, and these are known to be carcinogens, and those are just chemicals that cause cancer. Now, these cancer producing compounds are often formed as a result of heating organic materials to really high temperatures. They're present in tobacco smoke, automobile exhaust, and sometimes in burned or heavily browned foods. Such compounds are believed to be at least partially responsible for the high incidence of lung and lip cancer among cigarette smokers. Those who smoke heavily have an increased risk of getting cancer, and chemists have identified more than 4,000 compounds in cigarette smoke, including 43 known carcinogens. And so the EPA considers tobacco smoke a Class A carcinogen. Now, there are lots of uses of aromatic compounds. Most of these are predominantly in petroleum and coal tar. These are also excellent laboratory and industrial solvents. And then they're also really good starting material for a lot of other different polymers. Um, Another place we're going to see them as we get along into our discussion of nutrition is we are going to see these aromatic compounds in amino acids as well as essential vitamins. And so they will pop up again when we get to the biochemistry section of this course. So this concludes our discussion of aromatic compounds and alkynes. As always, if you have any questions, please feel free to stop by my office.